So thank you, Michael and team, for inviting me. I indeed started as a CTO at Corbion, but if you're nowadays a CTO, the spam email you get is all around artificial intelligence and all the IT stuff, right? So we decided to change my title to Chief Science Officer. And then we decided also to put sustainability behind it. So I'm no longer a CTO, but I'm a Chief Science and Sustainability Officer because it's a very handy combination to do that. So what I would like to do with you today is tell a little bit about our company, but I want to zoom out a little bit and really go for why, and that's a statement I want to make, and maybe that's an interesting trigger for a discussion later on. I believe there is no circular economy without a bio-based economy. And I will try to convince you why that is the case. And I think that is an important statement, because if we talk about it like that, then the drivers will be different. Because if I talk to traditional chemical companies, they go like, yeah, what the heck, you know, we have the circular economy, we will recycle everything, and so we don't need to change, really. But I think we can only do that if we also make the move to the bio-based economy, and I will explain that in a minute. So Corbion is a mid-cap listed company. We generate around 1.1 billion sales. That was last year. We are signed up for the Science Based Targets initiative. We are also net zero in 2050, and we have a path to get there, and it's a very ambitious path. What I would like to illustrate today also is that it in potential is possible to have below zero emissions if you go for bio-based. And I have one example where if you make PLA and you do it in the right way, with the right focus on yields and energy, you can actually stay below the amount of CO2 that you have absorbed in your raw materials. And I think that's a very interesting perspective. So we are looking at some major transitions going on right now, and John Bell referred to it already, and Christian as well. We have the energy transition, of course. We will see solar and wind. We have to do something with the overcapacity of sustainable energy that we may have, and that, of course, hydrogen is a thing that we see a lot as an energy carrier. Then raw materials, moving from oil to agricultural raw materials, or even ultimately going to CO2 direct, which would be great, that you can really take CO2 from the air and turn it into useful chemicals. There's a lot of publicity around CCU, and you probably have seen that in the news as well. I would say CCU is a high energy method to capture CO2, and then later on you still have to figure out what you do with the CO2. You can also say, why don't we use the green plant? The green plant is a CCU type of equipment, and it does it for free. The third one is the protein transition. And of course, we see agricultural protein, the pea protein and other examples, but also, let's say, precision fermentation to make protein of the future, where you really go like, what is the ideal protein that I could make? And then by fermentation or other means, actually make that protein. So these are three important transitions, I think, that will really influence, let's say, the society and companies at large in the next decade. So the example I would like to highlight with you is the production of PLA out of lactic acid. Corbion is a lactic acid producer. We have a joint venture with Total Energies where we are producing PLA as a potential replacer of polystyrene. As you know, a lot of the current oil is going into materials. It's roughly 4 to 5% of total oil consumption. The rest goes mostly into energy. So if we have alternatives for energy, then of course we have a lot of oil available, you could say, for making materials, but there are even better ways. So what I would like to focus in on is the circular economy, and this is a picture from the Ellen MacArthur Foundation, where basically you would like to recycle as much as possible. But there is, of course, you have to collect the material. If you make PLA, PLA is less than 1% of the total plastic amount that is out in the market. So for the plastic recyclers, PLA is actually a contaminant, not a raw material. So if we don't get it to 5% or higher, it will never reach that level, unless you team up with organizations that organize pop concerts, etc., and that have everything made out of PLA and that you have a centralized place to recollect it. So we have to think about that recollection system. Then the second is, you don't want to have plastic leakage. And even if you say we want to have the circular economy and recycle as much as possible, there will still be leakage. The discipline is not such that we will collect everything. And if we then leak plastic, we'd rather make sure that that plastic is in the end biodegradable. It has not to be gone in 2 weeks or so, but it should also not be persistent for hundreds of years. It's very important that we focus on that element as well. And that's a very complicated one, because if you say, I have a biodegradable plastic, you have a compostable plastic like PLA, we don't say that. Why don't we say that? Because if people throw it out of their windows because they think it's not a problem, it is a problem because it still takes 2 years to disappear from a natural environment. It is equally bad as a banana peel or a citrus peel, but we don't look at that. So it is a plastic, it shouldn't be in nature, so we should not waste it. So it has to be then recycled or composted in an industrial way. And of course, we like to decouple the plastics production also from non-renewable resources. And there bio-based comes in, or CO2 in the end, but that is not a technology that is ready at this point in time. So the example I want to show to you is PLA out of lactic acid. Lactic acid is a very versatile chemical. You can make all kinds of food ingredients from it. You can make solvents out of it for the electronics industry, as we do. You can make home and personal care products, but also PLA. And PLA is the most growing part of the company right now, double-digit growth, really picking up. We are sold out all the time. And we're considering building a second PLA plant, and therefore we also need new lactic acid production. So if you take polystyrene with a greenhouse gas emission of 2.2 kilograms per kilogram of product, and then you compare that to PLA today, where you have half, and we believe that if you improve, and I will show you some of those ideas that we have, the lactic acid production, you can actually go to 0 for PLA, and that means you have a negative emission for lactic acid. How does that work? So what we have, this is our current process in Thailand. So what we have the sugarcane fields. Those sugarcane fields, they fix CO2 from the air. It's non-concentrated CO2, just in the concentration as we have it in there. And we start them basically with a negative emission of minus 1,400 kilograms of CO2 per ton of lactic acid produced. Then we have to transport it to the factory. That factory is making sugar out of it, and they're using the remainder of the material, the bagasso, to generate energy and to supply electrical energy to the grid. So even that is negative. Then it goes to our plant, and there we have an emission of 600 kilograms of CO2 to do that. And then in the end, we produce lactic acid. For lactic acid, if you do that by fermentation, you make an acid. So you have to add a base to make sure that your microorganisms don't die while they're doing it. So we add limestone. And making limestone is a very energy-intensive process. So you need a lot of CO2, you get a lot of CO2 emitted to be able to do that. So in the end, if you take the whole, let's say, LCA analysis of this one, you take the full system into account, we come to an emission of minus 224 kilograms of CO2 per ton of lactic acid produced. That is cradle to gate. And so it stops at our gate. The end of life is, of course, an element that could still play a role here. If people would use it a single time and then burn it, then the CO2 is back, right? Then you have a different CO2 emission. But if you would use it in a building material, and you stop it for 30 years, and you put it for 30 years in a household, for instance, as an insulation material, then it's actually stored. Then you have a net negative emission of the lactic acid. So where are we heading? Because this is our current process that we have in Thailand. We are implementing right now, we're building a new installation that will no longer use lime to buffer the fermentation. So we don't have lime anymore as an element in there. We want to use full renewable energy. We're actually looking also at hydrogen in Thailand, which surprisingly is available today. That is blue hydrogen, it's not green hydrogen. Ultimately, we would like to use green hydrogen. But that's a possibility too. And if you have full heat integration, we could actually get to minus 1,000, over 1,000 kilograms of CO2 emitted per kilogram of lactic acid produced. Again, cradle to gate. So in principle, if you do your fermentation and you count the CO2 that is fixed in the plant with it, you can get to negative emissions. But here's an issue. If you look at the ETS system that we have currently, it only takes into account scope 1 and scope 2. The front end of this process is scope 3. So it's not taken into account. And that means that it doesn't matter now if you use a petrochemical feedstock or a bio-based feedstock, you really start from the same position. And I think that is a thing we should change also in the regulatory environment at the EU level. Otherwise, we would never make the transition to bio-based and will not be able to realize that bio-based economy. So for me, biomass is key to meet the COP21 targets, to be all in line with the Science-Based Targets Initiative. that we have signed up for that is really making sure that industries are moving in line with the targets that we've set in the Paris Agreement. We may have to use CCS, the carbon capture and storage, to make sure that we get there at some point in time. And the whole thing of carbon capture and utilization, which is now also you could say it's a bit of a hype right now, using unconcentrated CO2 from the air takes a lot of energy to do that. Why don't we focus on the green plant that does it for us? And I think that is very much an area where we should go for. The other element, and I've highlighted that in the last one, if you are using biomass, then please make something useful out of it. If you make fuel out of it, of course that may be useful, but the CO2 is then directly coming back into the atmosphere. You would rather like to make chemicals or materials in there that you store for a longer time. And then there's also the element of recyclability. If you recycle such a material, you avoid new oil that is being used. Again, that avoidance of that oil is currently not being counted in the CO2 system that we have. So reuse of plastics, and especially if they're bio-based, is also an element. If we would really do the administration well and have a good CO2 price, then I believe that the bio-based economy will really have a much higher pace than we currently see. And then there's the element of permanence. And I don't know if you've heard that term, but recently when I was visiting Brussels, there was quite a bit of discussions on permanence. Permanence is the element that tells you how long is the CO2 that you fix actually not being emitted again. If you have it in a building material, it's there for 30 years. If you recycle something 8 or 9 times, it could also be 9 years, could have 9 years of permanence. I think we should also go for that direction, that we really start counting that, because it really is only fair that if we take CO2 from the air and use it, that we also have the administration in place. Because currently, the advantage of bio-based over petro is not really visible in the way we administer our CO2 emissions. So with that, I'd like to stop, and thank you for your attention and the time.
Thank you, Marcel.